Let there be a radioisotope with a half-life of 300 days, and it is removed with a biological half-life of 150 days. So what is the effective removal constant and the effective half-life of the radioisotope? So first what we can start out with is our handy-dandy equation with the decay constant. So we know for a radioisotope, our decay constant, or lambda, is going to be equal to the natural log of 2 divided by the half-life of that radioisotope. So now we know with every radioisotope, they each have their own half-life. So then they'll each inherently have their own decay constant. Now, with biological interactions with radiation, so this could be, let's say, ingestion, like inhaling, let's say, radon-222. It seeps up from your basement. It could be in your lungs, or it could be from radiation therapy, perhaps. Well, essentially what happens is you have radioisotope decay, which is natural, inside a biological material, but you also have biological excretion also removing the radioisotope from your system. So that's where this effective removal constant and effective half-life comes into play, because you're taking into account both your natural radioisotope decay, but also your biological excretion as well. So it's essentially accounting for both of those removal processes at the same time, and that's where the effective half-life and removal constant comes from. So let's try to do this calculation. So we can start off by saying that the effective removal constant, or lambda sub e, is going to be equal to our decay constant of our particle, or our radioisotope, plus the decay constant of our biological process, essentially. So what we can do is we can use this relation from before, and we can write that the natural log of 2 divided by the half-life of our essentially effective, or our effective half-life, that's going to be equal to natural log of 2 divided by the half-life of our particle, and then we'll just say plus natural log of 2 of the half-life, or biological half-life, I should say. So you can probably see what we can do next. We can cancel out now our natural logs, and then that'll help kind of clean up our equation a little bit. And then what we can say is 1 over our effective half-life is going to be equal to 1 over the half-life of our particle plus 1 over the half-life of the biological process. So now what we can do is we can write our equation like this. So we can essentially invert it. So we can say that the effective half-life is going to be equal to, so we can do 1 over, so our particle half-life, which we said before was 300 days. So we'll say 300 days. And then this is going to be plus 1 over our biological half-life, which we said was 150 days. Essentially write that out. And then this will be to the -1. So now from here, what we get is a effective half-life of 100 days. There we go. Now we're halfway there. So now what we can do, now that we have our effective half-life, is we can use this equation to get our decay constant, or our effective removal constant. It's essentially the same thing. So now what we can write is that lambda sub e is going to be equal to the natural log of 2 divided by our effective half-life, which is going to be equal to, I'll write this a little bit longer, see why. So we'll have natural log 2, and then we'll have 100 days. But for this, we need to try to get this to seconds. So we'll have 24 hours in a day, and then we'll have 3,600 seconds in 1 hour. So those cancel out. And then that leaves us with an effective removal constant of approximately 8.023 times 10 to the -8 per second. And we're all done.